Okay, welcome. So this is the same announcement as Monday. We have the assignment 7 with the upcoming deadline. And we have exercise classes tomorrow and Friday. Okay, so today's lecture, we will have a lot of calculations to do. A lot of them are quite, actually they are straightforward, but a bit messy. So what I plan to do is I will do some and I will let you complete the rest, because the materials today are actually very fun. You can try to use some intuition to guess some limiting cases of the solution. And I would like to focus more on this kind of physical intuition rather than doing derivatives. Okay, I will do some, and I guarantee you that you should be able to do them yourself. You will be able to do them yourselves. And you are encouraged to do them by yourself anyway. You have to go through all this process at least once. Okay, so that is the plan for today. And I would like to start by showing you this slide. This is something we did last time. A lot of symbols, but not too bad. So we should start from here really. Okay, so this is the two multipliers that we attach meaning on Monday. So we first have the alpha, which goes with the number, is one of the Lagrange multipliers. So alpha goes with number, beta goes with energy. So this is something you should remember for this course. They will show up again. Okay, alpha goes with number, and this we established that alpha is basically related to some kind of normalization. Okay, and then we have this, which we spend quite a bit of time to derive. So this beta is related to the inverse temperature, as shown. Then we define this partition function. So this is really a definition. And why do we define it this way? Okay, well, you can understand this from the symbol used for this function. That is, we want to sum over all these exponential factors. There are so many of them. So one thing is to come up with a neat way to write them. You can also think in terms of the term we use to call this. We call this a partition function. So this basically tells you, if you know the energy spectrum for your system, the system you are studying, this eventually will tell you how to partition your energy. Okay, so you are going to partition it according to this formula. Okay. And from here, once we define, so this is the definition, we derive all kind of function of states. Okay, the first one is not really come from very profound derivation. You just rewrite the expression for n sub j. So this comes from the fact that we rewrite n sub j, which is really the goal of doing this, right? So why do we care about this business? We want to know the occupation number for a particular energy level labeled by J, so epsilon J. So this turns out to be related to this. This expression, right? If you plug in, if you don't want A, you do N divided by Z, then you see why. You get a better meaning of this partition function. Okay, and then we derive this last time. And we are going to look at this again today. So don't forget this. And these are the equation numbers written in the notes. Okay, so If you spot any error, please let me know. And by the way, I'm about to replace the PowerPoint for the previous chapter, chapter 8. Right now it's still draft. I made one, I think somebody found one mistake, so I corrected that. If you have more concerns, please let me know. I will make replacement soon. So I want to replace them soon, tomorrow. So please let me know. Okay, so before I move too far, we just need to very quickly talk about degeneracy. So far we have assumed our energy levels are not degenerate. So that is to say, I can just line up my energy level like this, and these are unique energy level. Okay, and what happens is we need to think about how to deal with degeneracy. Suppose I have a unique epsilon 1, and epsilon 2, I have two boxes that I can put my particles. Then this is twofold degenerate. So how do we do this? Okay, so let's answer this question from partition function. So the single particle partition function, for suppose I only have 3 energy levels like this will simply be e to the epsilon 1 divided by kBt plus and then the last term. Okay, I'm not going to keep writing this again and again, but you will get used to it. We really need to do a lot of this for this course. Today you will see a lot. Okay, so this is the partition function, single particle partition function for this problem. Okay, this is coming from this definition, but I want to expand this definition to include degeneracy. So how do I do that? This is the partition function for the bottom case will simply be epsilon e to the minus epsilon kBt plus e to the minus epsilon 2 kBt. Now I have to sum over everybody. I have to sum over all possibilities. So I will have to add another term, which is e to the minus epsilon 2 kBt. Okay, so I can also just group them together like this. Okay, so you have twofold degeneracy is 2. So this is a 2. And if you have G times degeneracy, then your partition function will include this factor here. Okay, so if you include degeneracy, so suppose epsilon j is this much degenerate, then the partition function is simply rewritten like this. So the single particle partition function is simply sum over j and e to the minus epsilon j kBt. Okay, you can see this is a consistent way to do things. Okay, you might be worried. Once we do that, how do we deal with all these thermodynamic functions we derived earlier? Okay, let's first look at what happens to this n sub j. N sub j will have to be modified slightly, right? Because n sub j now, you will have more ways to give to contribute to this quantity. How many more? That depends on the degeneracy. So in the end, this is just A times G degeneracy times this. Okay, very intuitive. Okay, and then the next thing is, what about all these variables? So first, let's look at the total number of particles in the system. So you really just plug it in. This is the definition, and you plug in with the new formula here. So you have sum over j, a, g sub j, exponential of minus. Okay, and then you see that your a can be pulled out. You really pull this out in front of the summation sign. You put this out in front of the summation sign, and you recognize the rest is the same symbol representing the single particle partition function. Okay, so from here, you can keep going and repeat the exercise we did last time, and you will discover that U, S, F, the Helmholtz function, etc., are identical. Okay, so this same expression as before. Okay, the thing is, this we talk about this sausage machine. So what you modify is the ingredient. So once you correctly account for the degeneracy, the way to calculate these functions remain the same. So same expression as before. Let me give you the number. So these are 922 to 924. 922 to 924. Okay, so it's just simply the way to count. We count it, count the degenerate states g times, and the result will be the same. Okay, now this is just to take a note about this. And this is more important. This is something we will use again when we look at gas. Now we are still talking about distinguishable particles. So when we look at gas, this will become very important to distinguish. So let's spend some time to look at this. In my note, I present one method to discuss this. Okay, I will define the problem. In the note, I discuss one way to do that. Okay, look at it. And then here, I'm going to show it, to do it in a different way. It's less rigorous, but hopefully more intuitive for some of you. Okay, the M is this. We have been talking about this single particle partition function. This is one way to look at the problem. And then the other thing I can also do is to look at all these M particles as a system. And I want to write the partition function for this system. That is why I use this symbol. Right? This is Z sub N, which is about the entire system of N identical distinguishable particles. Okay, so let's the M is to find the relationship between the two. Okay, so here let's write here. Okay, so what do we want? We want to look at the differently. We want to find the partition function for the entire system. What do I mean by system? Okay, this is a system of N identical distinguishable particles. Okay, let me do it this way first and do it rather slowly to make sure you get it, and also to give you a a glimpse of the future. So what is the future? The future will be, I want to generalize it later to delete this word later. But later means maybe next week, or hopefully next week. I hope it will be next week. Okay, so in the note, page, wait a minute, page 15, I give you one method to do it. Okay, so this is a little bit more abstract, but not too bad. And now I'm going to do it differently. Okay, let me give you a preview of the result. Okay, I take it back. I don't want to preview it anymore. So I'm going to write you this result, but I won't link it to here first. Okay, so what do we want to do? Okay, in the spirit of partition function, what do we want to do? So first, I'm going to look at a bunch of exponential factors, right? This is a bunch of exponential factors. Okay, now I can put in the degeneracy. Let me see. Now, okay, I will put in the degeneracy first, but for this argument, it's not that important. In the note, you get the one with degeneracy. Okay, don't worry too much about that. But what we want is to look at this kind of exponential factor. And we are basically summing over all m's. Okay, so it depends on how you call your m's, but you should imagine it this way. You should imagine this E sub m to be all kind of possible energies for n identical distinguishable particles. Okay, so before we have n identical particles, right? So why do we call it single particle? We only look at the energy spectrum, let's say energy spectrum, for one of them, right? This is particle A, this is particle B. Identical particle, but we managed to distinguish them because we can imagine putting these particles on a lattice, which we can give them the address. Right? This is the way to think about this. Okay, so this is identical spectrum, this is identical spectrum, and we look at one of them, and we know all the other particles behave different in a similar way. So we look at the single particle energy spectrum. But here, this EM is the energy, possible energy for this joint system. And we need to learn how to write this down. So I will consider exactly this picture drawn here, A and B, and to show you the result. So first, I will write, I will ignore degeneracy. Okay, this is just a different way of counting. So I'm going to call this, let me be careful. This is energy of A and B. So this will be E1B, and the second one will be E2B. I'm going to use a number to label different levels. So here, and this symbol, this alphabet to label which particle. So this here will be epsilon 1, A, epsilon 2A, and so on. Okay, and I'm going to set G to be 1. Okay, it's just a practice. Now the goal is to link these two. So we need to give the expression for single particle for A. Okay. Now this is just a bunch of exponential factors. And I'm going to go back to this symbol beta. I need to write a lot today. So this is epsilon 1A. Okay, so how do you do single particle? You go to this corresponding particle. read the energy spectrum, plug it into your exponential factors, and that's it. So this is epsilon 2a, and so on. Okay, and you repeat the same for B. Right now, please just assume they are different, because later, if we want to consider a general case, so we can see the pattern. So this is 1B plus 2B plus. Okay, so far there shouldn't be any problem, right? Okay, now the fun thing begin. The fun thing is, how do I write this? Now, I already, once I know how to do this, I have this expression. Okay, so first, this EM. Now, actually, I don't want to label M because M is already used. So I'm going to say this is the system energy. This is a system of two particles for this case. Okay, what are the possibilities? So the possibility will be this. This will be whatever the energy of A that you can have plus the energy of B. Okay? That is why we call this an assembly. This is an assembly of two particles, two single particles. Okay? So this EB, now we want to account for all possibilities, right? So this EB will come from this list. So this is E1B, one of this, E1B, E2B, E3, epsilon 1B, epsilon 2B, epsilon 3B, and so on. And likewise, you have the same for A. So the idea is you have to consider all kind of combination, all kind of possible combination when you do this sum over all possibilities. Okay, so now let's sum over all possibility. This one I won't write. Okay, I will write. I think it will be helpful for you. Okay. Okay, I'm going to do this operation now. Okay, now I want an expression for Z. How do you do this? You need to sum over all possibility, right? So let's do it systematically. So first, I will need to make sure I don't miss anybody. So I will need to be very careful. I'm going to pick E1A first, and then I'm going to change the second entry here. Okay, so this is for my first row. Okay, so I'm going to write a bit more for you. Okay, so I'm going to keep E1A, but I'm going to keep changing the second entry for B. Okay, the list is long, very long. Okay, so after I'm done, I'm going to then look at E2A. I'm going to pick the second element and then combine with all these elements in this list one by one. So each one will give me one exponential factor. So I will have E1B, this is E2A, sorry, epsilon, sorry, epsilon, I meant epsilon. Okay, and this list is long, very long, and I will have more. Okay, now you see the pattern very quickly, right? Because if you look at the first row, you see you can pull this out, 1a. And this is this first term is the product of two exponentials. One is e to the minus beta epsilon 1a times e to the beta, e to the minus beta epsilon 1b. Okay, so I can pull this out, and I end up having e to the minus beta epsilon 1b plus e to the minus beta epsilon 2b. Okay, this is for the first row. Plus, now I do the second row. I have e to the minus beta 2a, and I have the identical entry for the second row. Okay, and I can keep going. Okay, what is this square bracket here? This square bracket, sorry, I pull it down a bit. This square bracket is the same as this in green color. Okay, this is single particle partition function for B. Okay, so all of this will have this common factor, so I can pull this out. Once I pull this out, I have the sum of this. What are the sum of this? This is e to the 1a, epsilon 1a, epsilon 2a, epsilon 3a. That will be the line above epsilon 1a, epsilon 2a, and so on. Okay, so in the end, the result is a product of this. Okay, and now I invoke the fact that we are talking about n identical particles in n identical energy spectra. So there's no reason why A and B have to be different when it comes to energy spectrum. So one thing I can immediately see is that they are the same. So I would drop the label for them, and I will get this result. Okay, so really this is a two-particle system. I should label this as Z2. Okay, and in the note, the general result, if you do it more generally, using more algebra, not very different from this kind of argument, you get this result. Okay, so that is to say, if you choose to look at your system differently, you will be discussing the partition function for the assembly. And this is related to your single particle partition function by this formula. Okay, that's all. Now, why do we bother with this? The reason is we want to, sorry, this is what? We want to look at this again. Okay, and you will realize something. Now, every time when you see this single particle partition function, it goes to the log, and there's this n in front. N is a constant, so you can move it inside this partial derivative and raise it to become the exponent. Okay, so what have we found? So what we found is this result, right? Okay, it's just a different way to look at the system. So surely my energy, my entropy, my Helmholtz function must be the same. And the good news is really The reassuring fact is whenever you see this log, there's an n multiplying it here and here. So that means you can do it like this. You might as well write it like this. And you move this n inside and raise it to the exponent. Okay? And if you choose to look at the system as an assembly, you will have this. Okay? Now suppose you don't know anything about this equation. You plug it in. You have the expression and you do the calculation. You better get the same energy. Okay? This is the way to look at it. And here I won't write the intermediate step. So what you see is the same. You have KB log of Z sub n plus U over KBT. And here you have a minus sign, KBT log okay. Okay, if this is the same result, why do we bother with this? Now, listen carefully. Listen carefully. Now, this result written in blue color, light blue. Okay, so let me write this here. Now, if you only have very, very weak memory, you are only able to remember one equation rather than two for each thermodynamic function. Please remember the blue one. Okay, the black one, of course, is correct, but remember the blue one because the blue, these results are the same expression when we come to discuss gas. Okay, so let me make this remark. So this is a very important remark. So the expression in blue color, that is the one, those with this are applicable for indistinguishable particles. Okay. All right. So actually, if you are following me at home in the video, do not stop here. Okay, I'm going to write something else. Do not stop here. Okay. Let me change color. This is a bit unfortunate because I use the same blue. I meant light blue. Okay. Okay, now why do I change color? Because if you have indistinguishable particle, now if everything is the same, then there's nothing new to learn. What is the difference? The difference is there when you learn indistinguishable particle. So I ask you to remember this moment. When you meet the problem of indistinguishable particle, you will see this expression again. They are identical, but you have to write the system partition function very differently. Okay, so this is true. This is true only for distinguishable particle. Okay, so here, let me continue. So this is the same blue, right? This is what I want. This is the light blue. Sorry. It's very crowded here. Okay, but there you will see that you can still define the partition function for the system, no problem. You can still define the partition function for single particle, but you don't get this relationship. Instead, what you get is this, divided by n factorial. Okay, so this is a preview. That is to say, if you start from the energy spectrum, you correctly write down the partition function for the system, then you can use this expression again. Okay, now we will see why later. Don't worry too much now. But right now, please keep in mind what do we need to, what message do you want to take home from here? The take home message is for the distinguishable particle, this is true. For the distinguishable particle, this is true, and this is true. Okay. For the indistinguishable particle, this is not true. This is true, and these are true. Yeah. Okay. Again, this is also a little bit misleading. I should change color because here I assume this form. Now I feel like a kindergarten kid. When I first learned how to write ABC, I did a lot of this, tracing it. Okay. Is it okay? No problem, right? Okay, no comment means happiness, I hope. And this is fun stuff. And the more we will begin to do more example, and you will find a lot of very cool stuff that you can justify from intuition. Okay, so I'm going to we are going to learn how to play with this. Okay, so let's begin. I'm going to look at a two-level system. Two-level system means I only have two energy level. Right? So remember, from now I only draw one copy. There are n copies of this. Okay, so this is like this scenario, this picture here. But now I don't want to look at so many levels. I only want to discuss a system with two levels. Okay, and this is a very typical example. There are several variations. One variation is you call the lower energy level 0, you call the upper energy level epsilon. This is very common. You see in public exam, you see in final exam, material related to this course, okay, or some of the textbook. But for me, I would like to do it a bit differently. I would like to put it symmetrically about 0. Okay, I'm allowed to shift my energy like this. So I'm going to call this delta over 2 minus delta over 2. Okay, and the separation between them is delta. And another variation you can have is delta and minus delta. You have all this very standard variation, but the way to solve this problem is the same. Okay, the reason I do it like this will become clear very soon. Okay, so what do I want to do? I want to find everything about this system, all the thermodynamic information about this system. That is to say, I want a U, F, S. Okay, at this point, this is really an application, and you will see a real application. And then the common questions I always ask is, how do I know I'm correct? I develop all this methodology. How do I prove it? How do I design an experiment to find to prove my reasoning? Any guess? I have a two-level system. I'm going to begin to do some theory. So your friend is an experimentalist. What do you ask your friend to measure to prove that you are correct? Anyone? You can send to me in private. Spins. How do you measure spin? Okay, I'm going to tell you the answer. This is a standard answer for this course because you have seen it many times. I'm going to ask you to measure the heat capacity. And for this micro-canonical ensemble, I do not allow my volume to change, so this is CV. Okay, so I'm going to ask you to, hey, give me this result, this data, and I will be able to fit it to my expression. Okay, and please appreciate this statement. I can have a two-level system. I want to know the two-level system. What I really want is this delta, which is the energy spacing. Okay, so suppose I suspect that I have a two-level system, and from your data, I can extract the separation between them. So I basically have the full understanding of my microscopic understanding of my system. Okay, and Poon says spins. Indeed, spin is spin 1/2 is a classic example of a two-level system. Okay, so I will use delta. I will go to spin soon. Okay, the steps. What are the steps? You will see it very. Now you should be able to guess what I want to do. So the first step is to prepare the ingredient for the machine, for the sausage machine. Okay, what is this? Let me first write it down, and I will begin to stop writing all this detail. Okay, this is the definition of the partition function. This is my ingredient. And I come and read this energy spectrum. I know, okay, I have the degeneracy of 1 for minus delta over 2. Okay, so I plug it in. And then I have another one which I need to consider. That is this level here. So I plug it in. I have this. That's it. Okay. So there are different ways to do this, but I would like to do it using a hyperbolic cosine function. So I have E, so to remind you, EX plus E to the minus X divided by 2. This is cos, hyperbolic cosine X. Okay, so that has the advantage of if you know how to work with this, you know how to take the derivative. It will be fast. Otherwise, you can stay with this. Okay, so this will give me this result. Sorry, x is delta over 2kBt. Okay, and 2, what do I do with 2? I want the internal energy. Internal energy is very well known. This is very famous. I take the partition function. I take this partition function and plug it into this formula. I will be able to get my internal energy. Okay, so I don't know how much I should write. I would just write a bit more. Okay, I take the log of this, so I have log 2 plus log of cosine. Okay, and this one, this constant term will be gone. And this cosine, when you take the derivative, it becomes sine. Sorry, I think I will write still a little bit more. Okay, I want to take the derivative with respect to temperature. Okay, so I have a log, so this will give me cosine, everything inside. Okay, then I have to differentiate cosine, I get hyperbolic sine. Then I have to differentiate everything inside, I get delta divided by 2 kb. Then I differentiate 1 over t, I get minus 1 over t squared. Okay, you have sine, you have cosine. This will give you hyperbolic tangent. And the end result is, so there's a minus. Don't forget this minus. And delta over 2. And then hyperbolic 10. Okay, I hope I haven't made a mistake here. So let's see. So I have kbt squared is gone. This is n over 2. This is delta here. Sine over cosine. It's correct, right, guys? Yeah, I think so. Okay, and then you can go on and get your entropy. This is in the notes, so look it up. Right now, if I just write it, I will just copy from the notes. Not very meaningful, but you can do it yourself. And then the rest. Okay, in the notes, you get everything. And maybe I write one for you. This is the CV. Okay, how do you get this? You know the energy, so you just take the energy with respect to V. So this is guarantee in this ensemble. So you differentiate this, you get NKB. Okay, now this expression are given in the note. So this expression is 9.39, and this one is 9.37. Okay, so 9.37 and this Helmholtz function, these are really coming from plugging in the partition function. You plug in the partition function, use the formula we derived on Monday, and I repeated, I show you today. It's a bit long, but you get the result. And then this one comes from the derivative. So after you get your U, you can get the heat capacity. And this is the result. Okay? All right, so this is a standard example. Another version of this example is spin 1/2. Okay, so spin 1/2 will have exactly this spectrum. That's why if you spend a lot of time to work on this, the effort will not be wasted, because you can simply replace your delta by the appropriate energy spectrum. You would just, everything would just, you can just copy and paste and change the symbol. Okay, so I'm going to present this problem, and then we are going to take a break, and we are going to look at this problem carefully. So this is a paramagnet with spin 1/2. Okay, so the spin quantum number is ms, and you have ms equals 1/2 or minus 1/2. Okay, and you know in the magnetic field in your quantum physics, you know when you apply magnetic field, you have two energy levels. Suppose your particles, let's don't say too much about what kind of angular momentum. Suppose you have a G factor. This is not degeneracy, so this is lambda G factor. Let's take it to be 2. Then for spin 1/2, your energy spectrum will be G times ms. So this is your energy spectrum will be G times ms times mu bb when you apply a magnetic field B. Okay, so this will give you plus or minus mu bb. Okay, so I can draw this picture now. I will draw it like this. This is mu bb, and this is, sorry, this is minus mu bb, and this is plus mu bb at the top. And this is the same as what I discussed earlier. I use delta over 2 minus delta over 2. So now you know why I want to put it symmetrically. So I can just analyze a spin problem very quickly. So I only need to go back and replace delta over 2 by mu bb. Okay, so before the break, let me say a little bit about this. This is a very interesting problem. I really like it. So what is mu b? Mu b is Bohr magneton. Okay, now for this course, it will be fun to pay attention on the number. So this is 9.27. 10 to the minus 24 in SI unit. Okay. Now this is the energy scale given by the magnetic field. You can think of it this way, right? So this is an energy scale which is more or less determined by my external field. If I apply 1 Tesla, the splitting will be of the order of this times 1 Tesla. Okay, and for thermodynamic, our energy scale is set by Boltzmann constant. And look, what is the size of Boltzmann constant? This is 1.38 times 10 to the minus 23. Okay, and put the unit. This is Joule per Kelvin. Okay, these are actually very, very close. Look at it, this is nearly 10 to the minus 23. This is a large number, 9 for this order of magnitude. Okay, so these two are comparable. And therefore, you can really discuss the interplay between the two energy scale, the field energy scale and the thermal energy scale. And when they are comparable, that is when you see the most interesting physics. Okay, so we are going to look at this after the break. Let's take a break and come back at 1:35. Okay, so before the break, we set up this problem. And as we discussed, we simply have to replace this delta over 2 by mu bb. Okay, so all this expression we developed here can be used. Okay, I just want you to know how I get them, and I will not derive them again for the spin here. Okay, and instead I will just write them down and discuss the physics. Okay, so U, the internal energy. After I make this replacement, you see, you remember there's a minus sign, and this minus sign is important. and mu BB tangent of mu BB and KBT. Okay, so this justifies what I said earlier. That is kind of important to have some feeling about this number. So this is mu B. Let's write it there. Sorry, this is mu B. Okay, they are similar, right? And then we count our field. We measure our field in Tesla, 1 Tesla, 2 Tesla, and then measure our temperature in 1 Kelvin, 2 Kelvin. So this is the same. Can be the same order of magnitude at low temperature in particular, right? It's not that difficult for us to apply a magnetic field up to 10 Tesla. If you want a magnetic field of 100 Tesla, good luck, that will be harder. Okay, so this kind of interplay will be very interesting to observe at low temperature. Okay, low temperature means of the order of a few Kelvin. That's low enough for this. Okay, so what do I want to do? Now, first, can you understand this expression? See whether you have some feeling about this. Let's develop some intuition with respect to this kind of energy spectrum. Okay, remember how we calculate energy? The way we calculate energy, if we go back to very, very beginning, we count how many particles are occupying a particular energy, right? We do this accounting, which I'm always saying. Okay, so for this to work, you need to apply a little bit of magnetic field. When there's no magnetic field, you cannot leave the degeneracy. There will be twofold degenerate. Okay, you apply a bit of magnetic field and you have this behavior. And we always like to discuss the limiting case like this. Limiting case means we're comparing these two energy scales. So at low temperature limit, so low T limit, what do we have? Low T limit means my KBT is much, much smaller than mu BB. Okay, for this course, this part, I would like you to imagine this to be the separation between the two levels, right? To be proportional to this, up to a factor of 2. Okay, it's a little bit harder if you don't think about it this way. If you only regard this as the label for one of the energy levels, then it's hard to have a good picture. So just think of it as the separation between the energy levels. Okay, so if KBT is very, very small, low temperature limit, what you are really doing, this is increasing temperature, increasing energy. So you don't have that much thermal energy for you to populate the upper level, right? So in the very, very low temperature, I will draw it for you. So this is the field energy scale. This is field energy scale, which is mu B minus mu B, as mu BB minus mu BB. So this is about, this is 2 mu BB, but this factor of 2 is not that important for us. Okay, now your thermal energy scale should be compared, right? If my thermal energy is very small, this is my KBT, then I really do not have much chance to occupy the high energy level. Okay, so in this case, I should expect many particles, spin 1/2 particles, to be in the lower energy state. Okay, so each one will give me mu BB. So if I have n of them, I will have n times this level. So I should be able to extract to the limiting case of this prefactor. And indeed, you should be able to work this out yourself. So to help you, I'm going to do it in several ways. So to help you, I'm going to remind you about the curve of tangent function. Okay, this tangent will saturate at 1. Sorry, hyperbolic tangent. This is not our usual circular function. Okay, so this is 1, and we have a -1 here, -1. And at the large x limit, this function saturate like this, like this. Okay, and at the low x limit, this function behave like an x. There's no bump here, sorry. Okay, so at the low x limit, this is like a straight line with a slope of 1. Okay, so tangent is like x. With this, you will be able to work out the limiting case, large x limit, low x limit, by considering the appropriate limit. Okay, now but before we do the mathematics, please try to understand why the physics is like this. Okay, I already told you one. What about the other limit? The other limit is when your when KBT is much larger than mu BB. Okay, so the other limit, this is high T limit. What do I mean by high T? I compare the energy scale again. So I want this limit. So in that case, this is still the same. This green arrow is still the same, but my KBT is huge. Imagine it to be from here all the way to the bottom of the screen. So in that limit, I do not really care about the separation anymore because I cannot see. This KBT is so huge. I cannot see this fine detail anymore. And I should expect them to be equally probable for occupation. Okay, that is to say I should expect half of my particle to be here, half of my particles to be here. So if I do the accounting, my U better be 0. Okay, so let's write the result. So here my U has to be 0. And here my U has to be minus N mu BB. Okay, I justify this basically purely based on physics. And you are required, you are encouraged to analyze this mathematically. Not too difficult, 5 minutes or less. Okay, you should be able to do this after I give you all the ingredients. Okay, so this is one way, do it from physics. Second, do it using algebra. And the third way is to look at a graph. Okay, so this is how I plot this. I'm not gonna write it again and again. So I want this picture taken. This. Okay, so this is the function I plot for you. Okay, this is what I say. Let me explain a little bit. I like to plot it in the dimensionless way. So that is to say, I don't want this prefactor, so I move it to here. Okay, so I basically plot this function against t. So you can think of it as everything is fixed. I only change the temperature. So you can think of it as this function versus temperature. Okay, so then I can discuss the low T limit. I have a little bit of U. This is a fixed amount of U just to split the energy level, leave the degeneracy. And everything I say earlier can be verified here too. You see, this is the low T limit. I will have this ratio to be -1. Okay, I occupy only the lower level. And this T is hardly high enough. If I go to very high T, this will approach 0. Another way to look at this is to look at how, if you fix the temperature and vary the magnetic field, what happens to the internal energy U. Okay, so here, if you have a ruler you will be able to put it in front of your screen, and you realize this is this part of the curve, the high field part of the curve, not very high, but high enough here. This is linear. Okay, so this is a curve with a slope of with a slope of 1. Okay, so this slope is 1 here, this part. So if you go to high field, you will see this becomes very linear. Okay, so this is data analysis. You give me this figure and I look at this for a bit and I realize, oh, I have a linear region. Okay, what does it mean? So let's see whether we can understand this picture. So linear region, if you really try it, put a ruler and align this part, you will see this is a straight line with an intercept of 0 even. Okay, slope is 1, intercept is 0. So I know how to write this function. You see, this is my way of plotting it. You will see this means I will have, this is y, this is my x, mu b, divided by kbt times b, plus 0, intercept is 0. Okay, this is for high field, fixed temperature high field. Okay, now this is again understandable because look, if you do it this way, sorry, this is a slope of -1, so there's a minus sign here. -1, -1. Okay, so if you at high field, your energy U will becomes minus mu b times n. Okay, this is again a very cool picture. Why? Because okay, suppose you have two energy level like before. Okay, at some field which is low. So let's say you have some low field here. Now you fix the temperature. So let's say we fix the temperature for this discussion, and 1 is when these two energy scales are comparable. Okay, so in this region, you are talking about a field which is much smaller than kBt. So you really have the same situation as before. Okay, the field is much smaller than the mu kBt. So the thermal energy is much larger than the spacing between the energy level. So they should be equally populated, and you start from 0. Okay, now you fix the temperature and begin to increase the field. And what happens then is this will symmetrically move away from 0. Okay, so this is some field. Okay, and this is larger field, larger B. So it moves symmetrically away from 0. And your thermal energy cannot compete, cannot catch up. Right? So when you are much larger than kBt, when your mu bb is much larger than kBt, you just cannot catch up. You will always be occupying the lower energy level, and therefore your U is proportional to B, which is why you get this linear slope. Okay, it's larger field, and then another one, your field will be even larger, like this. So you cannot occupy this anymore. This is hopeless. This is moving so far away. And this get pushed below 0 further and further. Okay, and that explains why you get this behavior. Is it good? Is it cool? Okay. Now, if so, I want to somehow link back to what we learned when we discussed spin before in thermodynamics. In chapter 7, we discussed this problem. These pictures are not new, you have seen before. It's just a picture for you to understand when you apply field, what happens. And back then, now this is one thing, this is just a reminder. one thing I did was I told you there's some function like this. I didn't tell you how to do this, but now you should be able to calculate this yourself. Okay, now this calculation is a little bit more complicated because it includes the entropy from other contributions. But for this spin half system, you should be able to get S versus T in at least a qualitative manner. Qualitative in the sense that we are allowed to do adiabatic demagnetization using your calculation, and we respect the third law. Okay, that is to say my S has to go to 0 regardless of the field. Okay, so this is something we can do now in this part. Okay, so what is this? This is S, entropy. So we need to discuss the entropy now, the entropy of spin 1/2 system. Okay, again, I want intuition rather than mathematics. How do you do this? Really, how do you do this? If you really want to do it without much thinking, you can. Why? Because you know how to do S. So I'm going to take you through, and this is not what I want to do. Okay, so you come back here. You have this expression, right, which is 9.37. And how do you get this expression? This expression comes from here, up a bit from here, right? You know how to write the partition function for the two-level system, and you already calculated your U, which is also related to partition function. That's why I don't want to do it here. It's long, but you get this expression for spin half system. Okay, but I don't want that. I will give you the formula anyway. Let's see if I can find it in the note. Just give me a few seconds. I give you the formula to convince you that you can do it. Where is it? Where is it? Here. 9.41. Okay. This is 9.41. But this is not fun, actually, because we don't really learn much by just looking at this formula. Okay, so 9.41. 9.41. Okay, what can we do? I want your intuition again. Tell me, what is entropy at high temperature limit? Okay, and I would like some interaction here, interacting with me in private. And tell me how to get this. So now actually, how do you do this? You can analyze the limiting case, right? So you see this mu bb divided by kbt, mu bb divided by kbt. Okay, you can calculate S divided by nkb. So once you do that, you have, if you divide by n times kb, you have to divide this term by n and kb. So you basically have the same form here. So this is the ratio of energy scale, ratio of energy scale, ratio of energy scale. And you discuss the limiting cases for these terms. This is one way, and this is the proper way to do it, actually. But this is algebra. Again, the reason I spend time on the internal energy is I hope after you have seen how we handle the internal energy. You can tell me the entropy without doing this calculation. Okay, high temperature limit. Tell me. Okay, I get some nice answer. Thank you. More? Hmm? The rest are with me or not? How many of you are here? Okay, I want the reason now. I see a few correct answers, but I want the reason. Okay, now if you can guess, I got several answers and they are all correct. And the limiting case for this is indeed n kb log 2. But then we want to know why. Okay, now why? This is let me draw this cartoon again. I'm going to draw this situation. This is mu bb, and this is my kbt. Kbt is much larger than mu bb. Okay, imagine this is even larger. These two lines, this separation will be so small that I can kind of equivalently draw them like this. The truth is I do not have resolution to tell them apart. Okay, so essentially this two-level system in this limit is just like the coin problem. This is head or tail. Okay, so you in the coin problem we have head or tail, but we didn't assign which one is higher energy, which one is lower energy. We did all this calculation before. Okay, and you know how many number of ways for this to happen. If you have n coins, right? For each coin you can choose between head or tail, so you have altogether 2 to the n. Okay, once you have this situation, this is like a coin problem, and you know for the coin problem, this is the way, the total number of way to get this. Or you can, if you want to go through the full calculation, you can try to do it. You get the same answer, I guarantee you. Okay, and now you apply the statistical definition of entropy, our postulate 3 in chapter 8, and you immediately get the answer. So you get 2 to the n comes out, you have nkb log 2. Done. Okay, so this is one limiting case. The other one is this. I want S when kbt is much lower than mu bb. Okay, this you have two ways to argue about this. One is the is simply applying the third law. Okay, you can just say because the third law of thermodynamics tells us entropy has to go to 0 at 0 temperature limit, I will have this result. Okay, but it's good. But the other answer I like is an argument along this line. Okay, to say that there's only certain way to count. Okay, and how do you do that? That's the opposite of the coin problem. It's also, you can also think of it as coin problem. And now I really do have up and down. Okay, So my thermal energy is so tiny, right? That I can tell which one is up, which one is down. And according to my argument earlier, I know at this limit, all of my particles will want to occupy the lower energy state. And then if I assign this to head or tail, right now I need to really say which one is up, which one is down. I know I will only have one situation where all the N coins are having tail, or all N coins are having head, right? You remember that table I gave you? And in that case, your omega is 1. Okay? Omega is 1 in this case. And therefore, S is 0. Okay, the exercise for you now is this. This is the result. I guarantee you they are correct. And now you should verify this yourself, the limiting cases. Okay, using this expression, you plug in the limiting cases, look at the behavior of tangent, look at the behavior of hyperbolic tangent, hyperbolic cosine, and get this result. Okay, now coming back to this problem I mentioned, this one, you see, this is S versus T at different field. Now you can do it like this. This is S versus T at different field. You can fix different field and plot entropy as a function of temperature. And hopefully you get something really behave like this for you to link back to the part of adiabatic demagnetization. Okay, and I will show you my plot prepared using MATLAB. You can do it yourself. Right? It really goes like this. Okay, I plot again. I like to plot it like this: S divided by NKB. So this is in the unit I like. Why? Because I want to plot S divided by NKB. And as I say, once you do it this way, you can get energy scale here. Sorry, the energy scale divided by another energy scale. That will give you a way to compare them. Okay, if I plot it like this, this is basically entropy measured in the unit of NKB versus temperature. And you do see this behavior. So you can do isothermal magnetization and adiabatic demagnetization, like what we discussed before. Okay, so everything is now linked together. Okay. All right. Now I think this is the high point here. The next part is to derive Curie's law. Another promise I made when we discussed this. You see, we have this Curie law somewhere when we analyze all these partial derivatives back in chapter 7. And if Curie law fails, I wouldn't be able to discuss adiabatic demagnetization. Okay, so this is the power of knowing both thermodynamics and this microscopic treatment. Okay, when you combine them, you get something very powerful. Okay, so first, thermodynamics. I'm going to look at the differential change of the Helmholtz function. Okay, so this is given by this expression. And this expression is 7.12 in chapter 7. Okay, not very mysterious. We just changed the PV work to magnetic work. And we already derived this kind of expression. And this M, just to remind you, this M, little m, is moment, which is magnetization times volume. Or magnetization is moment per unit volume. Okay, how do I get Curie's law? I'm going to take the partial derivative, right? I know how to calculate m now because if I have this expression, I know m is defined like this. Okay, with a minus sign. Where should I put it? I will put it here. Okay. And remember, I know how to write f in terms of the partition function. So in principle, once I know the partition function, I know my moment because I can just take derivative. Okay, so remember f carries a minus sign, so there's a minus sign here. You better get plus. And this log. Okay, this is from the definition of partition function. Okay, and you get this result. You have, once you carry out, there are a few steps, obviously, then you get n mu b, tangent, hyperbolic tangent, mu b, b, kbt. Okay, why is it related to Curie law? And now you need to think a little bit. Now, when we talk about Curie law, from that picture I show you about the moment here, when we discussed this, we did mention that we do not want to saturate the moment. So we want low field, right? So if you want, Curie law is about susceptibility. If you apply a low field, what happens to the susceptibility? Okay, so how do we incorporate this low field? I remember somebody asked me this question back then, and I say, wait, I will show you in a few weeks' time. And here is the solution. So this moment in the weak field limit, weak field, and now you know how to handle weak field, strong field, high temperature, low temperature. There's you need a reference. The reference is you compare energy scale. Okay, so if you have weak field, what do you have? Weak field means mu bb is small compared with kbt. So this hyperbolic tangent behave like a linear function with an intercept of 0. Okay, this is this figure I gave you earlier. Sorry. Where is it? This. Okay, and low x, this is linear, and it goes to 0. Okay, so let's do that. So weak field, this is a small argument. I will have n mu b, and then another mu b, and I have field divided by kbt. Okay, that is almost there. You see the inverse temperature relation, 1/t behavior. If you want to really recast it in the susceptibility, you just define it properly. This is a big M, right? And then you see everything else just come out correctly. Okay, you just move a few symbols from here, from this equation, you will have 1/t behavior. So this is Curie's law. Okay, and I promise you, I don't want strong field because I will polarize everything and I will have saturation. I can also show you that. How do I show you that? I will have to look at the strong field limit. A strong field limit. What happened at strong field? At strong field, whatever happened here, this is large, and this tangent function becomes 1. So I will have n times mu b. Okay, why is it saturation? The reason this is saturation is the following. Now we are talking about moment, the total moment. The total moment becomes n times the individual moment that are parallel to the magnetic field. And for our spin half particle, the moment is 1 Bohr magneton each, and you have n of them, and they are all occupying the lower energy level, which is parallel to the magnetic field you apply, and there are n of them. That's why the total moment is this. So the strong field case is also correct. Okay, this is very satisfying, I find. Okay, next, that comes to the final part that we need to answer. What is the heat capacity? The heat capacity, again, you can calculate. And I want to focus on the physics. So how do you do that? You do the derivative. You have your u, and then you take the derivative. Okay, and if I plot it for you, it will look like this. So this is the heat capacity. Heat capacity versus temperature. Okay, the heat capacity will look like this. Now, first, from third law, you know it has to start from 0. What you see is this heat capacity will grow, and at some point it will show a peak, and then it will die down like this. Okay, this is this peak. In the assignment, I ask you to find the temperature where this peak occurs. And how do you do that? You analytically, you take the expression for CV, you do the calculus, you'll be able to find the temperature at which CV is maximum. And this has a name. This is called a Schottky anomaly. So this is Schottky anomaly. Now, to understand this, you need to look at this. And to understand the physics, you also need to know this temperature and express it in terms of the energy scales. Right? When does it happen? Okay, but again, we can discuss the limiting cases. These limiting cases is consistent with all the pictures we have been developing so far. What is heat capacity? Heat capacity is related to the change of internal energy when you inject thermal energy, right? You look at it this way, the change of internal energy in response to the injection of thermal energy. Okay, so here at the low temperature limit, I will draw this cartoon once more time. Okay, you give some thermal energy, fine, but this is so tiny, you don't really change the big picture much, because the particles here will not be able to take advantage easily and jump to here. Okay, so you really start from 0 and stay quite flat for a while, because you inject thermal energy. So this is finite, but U doesn't change much. It changes by very little. So this slope is very tiny, almost horizontal. Okay, and the other limit here, you have a lot of thermal energy. Fine, you give so much thermal energy, but you don't change the population either. They are already half and half of the particle here, half of the particle here. At most, some particle will take the energy to go here and some will relax back. You don't really change much. There's no other ways for them to go. So heat capacity will eventually go flat again. So you have a flat slope and you have a flat slope, and in between you have a peak. That's because when your thermal energy begin to grow, some of them will take advantage to go up, and that leads to the increase of U. So your heat capacity begin to get larger. Okay, so what happens in between is when these two energy scales are comparable and you have more messy situation to argue, but then you can kind of qualitatively see why it should go up like this. And what eventually, if it needs to come down, right? If it has to go up here and come back down to 0 here, so there must be a peak. Okay, so if you give me a temperature dependence of heat capacity like this, I can tell you that the energy spectrum must be finite. I must have only a finite number of energy levels, because otherwise it will not come back down. And next lecture we do harmonic oscillator. Harmonic oscillator is different. Harmonic oscillator, you have infinite energy level, infinite number of energy level, and use the same argument. It will start flat, and the heat capacity will grow when you increase the thermal energy. And I hope you can think about it a little bit more and see that if you have infinite energy spectrum, eventually the heat capacity will saturate. It will not go back down to 0. This slope will still be very small, but it will not be 0. Heat capacity will not be 0. Okay, so what is the message? The message is this: you measure heat capacity, you show me the heat capacity, I will be able to tell what is the energy spectrum of my system. Okay, this is this model is related to Einstein. It's Einstein's model for heat capacity of heat capacity. Okay, we are going to analyze this model on Monday. Okay, thank you very much.